Australia's Uranium Opportunities by Keith Alder. Recorded by Logan Smith with the permission of the Alder family. Chapter 4. Beginning of the AAEC Research Program. The Research Committee under Dalton had some preliminary guidelines set in discussion with Watson Munro before he left for Australia. It seemed logical that Australia should undertake research not being done elsewhere, to make her own contributions to the world pool of knowledge and, most importantly at that time in nuclear history, to have something to trade, to gain access to the information of other countries by having information to which they would like to have access. It was also intended that the research program should be designed to build up a cadre of experts in Australia. The detailed program should not be an end in itself. The training and development of expertise were to be the primary objectives so that the benefits of atomic energy could be brought into use in Australia. At the time, the emphasis in all major overseas nuclear research establishments was on the development of atomic energy for peaceful purposes, i.e. on nuclear power reactor development. There were many, several hundred, possible concepts of how the atomic pile could be put to work to generate useful power for industrial and domestic use. All were directed to generation of electricity by controlled nuclear fission. In the mid-1950s, new proposals for reactor types seemed to arise and disappear almost weekly as some scientist or engineer came up with another brainchild. At Harwell, some of these led to serious detailed work in theory and experiment, only to vanish and be replaced by other new ideas. For example, during our time at Harwell there was a heavy water moderated reactor proposal called HIPO, a light ordinary water cooled and moderated reactor called LEO, and for a while I worked on its fuel element, a liquid metal fueled reactor LMFR using uranium dissolved in liquid bismuth, a uranium hexafluoride gas reactor called Felix, and a graphite moderated carbon dioxide cooled reactor called PIPA. This latter was the only survivor of these and many others, and it eventually became Calder Hall, Britain's first nuclear power station and forerunner of the Magnox series of reactors in the first UK power program. It was a similar scene in the USA, Canada, France, the USSR and other countries, and when in October 1955 the first international conference on the peaceful uses of atomic energy was held in Geneva, and security on the civil atom began to be relaxed, there were many interesting concepts unveiled. It was a very exciting time to be in the field. The research committee members were reasonably well informed by this time on what was going on around the world in reactor development. The USA was leading the field in light water reactors, and Canada was well underway towards heavy water moderated systems. The French and the British were concentrating on graphite moderated systems, and so were the Russians, as emerged in Geneva in 1955. There was one promising neutron moderator not being studied in detail by anyone else, the element beryllium, and it seemed a promising field in which Australia could undertake both basic research and development, in a field not being tackled by others. The properties required of a neutron moderator, or slower downer, are that it should consist of light atoms, so that every collision by a neutron dissipates a significant amount of its energy. It is also very important for the moderator to have a low neutron absorption. The candidates are hydrogen and its heavy isotope deuterium, hence heavy water, carbon, usually as graphite, and beryllium. The next element up on the list, boron, is a heavy absorber of neutrons and is in fact useful as a controller in reactors. Within these ground rules, the committee recommended, and the Commission agreed, that the Australian program should concentrate on the use of beryllium as a neutron moderator, and initially should be studies of two possible power reactor systems, a high-temperature gas-cooled reactor, HTGC, and a liquid metal fueled reactor, LMFR. Both beryllium metal and beryllium oxide should be studied. In 1958, the government formally accepted that the Commission's research program should be a study of reactor systems, and it emphasised that the objective was to build up a cadre of experts on atomic energy in Australia. This objective was reiterated through the life of the reactor research program of the AAEC, but it seemed not to be appreciated by the principal critics of the program. The centrepiece of the program, the element beryllium, has some very interesting nuclear properties. As well as being a good moderator of neutrons to slow down the fast neutrons from fission so they can be captured in fissile atoms more readily. Some neutron capture in the beryllium leads to the production of yet more neutrons by an N2N reaction. There is also a N-alpha reaction. The alpha particle is a helium nucleus. Both of these reactions give the possibility of neutron enhancement, a favourable phenomenon in reactors, which could extend the fuel lifetime and we believe might even lead to the possibility of a thermal breeder type of reactor, producing more fissile atoms than it burnt. Beryllium oxide also has the useful physical property of being a good conductor of heat, and in fact is a better thermal conductor than beryllium metal, which is unusual. It is also a good electrical insulator, which makes it useful in today's electronics industry. The concept for an LMFR was to use a slurry of fissile material in liquid sodium, pumped into the reactor core where it would go critical and produce heat, and then be passed through a heat exchanger to raise steam. There was already considerable background knowledge in the use of liquid sodium, and the sodium-potassium alloy as a coolant, arising from fast breeder reactor research. The very high heat fluxes in fast reactors require special cooling arrangements, usually involving liquid sodium coolant. There were active LMFR projects at Harwell and at one American research establishment, the Brookhaven National Laboratory, both using solutions of uranium and thorium in liquid bismuth. Several of us visited this project in 1957. Unfortunately, liquid bismuth turned out to dissolve most other metals too, leading to difficult containment problems which we hope to avoid by using sodium. The HTGC program was to study dispersion fuels of the fissile and fertile materials, uranium and thorium, in the form of fine particles of their oxides dispersed in beryllium oxide. Although beryllium metal containing dispersed uranium and thorium was studied initially, it was soon realised that the temperature attainable would be severely limited by irradiation effects on the metal, including both embrittlement and swelling, the latter from the helium atoms produced by the N-alpha reaction mentioned earlier. These effects were in fact demonstrated at Lucas Heights later. In the early days of irradiation testing of materials in HIFAR, when beryllium metal samples were tested under a research contract with the UK Atomic Energy Authority, which had hoped to use the metal as fuel cladding in its Advanced Gas-Cooled Reactor, AGR. The reactor had to use stainless steel cladding, which was detrimental to its neutron economy and therefore to its economics. With the agreement of the Harwell authorities, we were able to commence some work on the AAEC program there in 1956. Theoretical studies in reactor physics and engineering began under Cliff Dalton. Some work was started by the chemists on dispersion fuels, and the metallurgists began to construct and operate experimental loops pumping round liquid sodium. They also produced very fine uranium powder. This was a project undertaken by Dr. J. W. John Kelly, and the product was so fine that it was highly pyrophoric, meaning it would catch fire spontaneously if exposed to the air. This caused several of us a problem at one stage, for we had a fire and inhaled some of the dense uranium oxide smoke. I can recall vividly the gritty taste of uranium oxide in my teeth when Frank Bett, John Kelly and I fought our way to the door of the laboratory at Harwell through that smoke. Then we were monitored by the health physicists for some days until our metabolic systems ran out of uranium. Our idea was to disperse this fine powder in the sodium, but a problem was the density difference, uranium being very heavy with a density of 18.7 and sodium relatively light with a density of 0.97, very close to that of water. Some analogue experiments performed later at Lucas Heights using a slurry of tungsten powder dispersed in water, which simulates the density differences almost exactly, showed that although it was feasible to pump such a mixture, there could be problems with deposits forming in parts of the circuit. It was hoped to overcome this problem by alloying the uranium and thorium with beryllium, which produced a much lighter compound of density about 4.5. In late 1957, the metallurgists managed to purchase most of their liquid sodium rigs from Harwell at a nominal price, and crated them themselves for shipment to Australia. This caused some interesting logistic problems. The bureaucracy of Australia House did not know how to handle this situation, so the metallurgists hired a truck and delivered the crates themselves into the Australia House basement in London, presenting the purchasing shipping section with a problem they simply had to solve, which they did, and the equipment subsequently arrived safely in Sydney, leading to some head-scratching by customs. But it all ended well, and gave a flying start to the liquid metal work at Lucas Heights. The return of the AAEC staff to Australia caused a few problems at Harwell, because some of them had become deeply involved in parts of the UK program, and their departure left serious gaps. When I told the Chief of Metallurgy Division, Dr. Monty Finiston, later Sir Montague, and head of British Steel, that I and my 8 metallurgists would be leaving within the next few months, he gave a wail of despair, which in a way was a compliment to us. However, he did ask specifically for some of the departures to be delayed for a while. For example, one of our group, Brian Hickman, was running much of the work of the irradiation group and would have left a difficult gap if he had left at too short notice. Brian left us later, in 1966, and worked in the USA for a while, then returned to Australia to be a Director of Research for ACI and later Director of the Australian Mineral Development Laboratories in Adelaide. The Atomic Energy Research Establishment Harwell had been very good to the Australian group, and all of us had made good friends amongst the staff. When we knew we would all be leaving before long, we decided to make a presentation to the establishment of some memento of our presence. So we took up a collection, and everybody subscribed. The total amount was quite substantial, some hundreds of pounds. A small committee was formed to recommend what we should buy, and they came up with the idea of buying an Australian painting. Dr. Jack Gregory was in charge of the purchase, and the group obtained 2 original Australian paintings in London, a Dargy and a Nolan, which we presented to Sir John Cockcroft for the establishment at an informal gathering. Cliff Dalton made the presentation. The paintings were hung in the stairwell of Cockcroft Hall, the main lecture theatre at Harwell. They must be much more valuable now than they were in 1957. End of Chapter 4. To all my Australian listeners, I have a favour to ask. Australia's energy policy is likely to be a federal election issue in 2019. I created a voter's message to the minister soundbite. If you support nuclear power for Australia, please forward it to your minister to show your support for this industry. More information and a link to the soundbite is in the description. Thank you. Australia's Uranium Opportunities by Keith Alder. Recorded by Logan Smith with the permission of the Alder family. Chapter 5. Early Research and Organisation at Lucas Heights. The Australian team trickled home during 1956 to 58, as buildings and facilities became available at Lucas Heights. I was the last section head to leave Harwell at the end of 1957, and I had the task of closing down the Australian office in Hangar 10. There was a combination safe in it, and Cliff Dalton had forgotten to give me the combination. The Chief Security Officer, Wing Commander Arnold, was summoned and sent for his deputy, Captain Potter, who proceeded to kneel on the floor and carefully listen to the lock as he twiddled the dial. In about 20 minutes he had the safe open. When we asked how he did it, he said he learned it during the war from an old lag in Wormwood, Scrubs Prison, who received some remission of a sentence as a reward. The contents of the safe turned out to be not really classified, as all we found was Cliff Dalton's lost pipe and Charles Watson Munro's income tax papers inside a file entitled Crazy Gang, which Charles had started to house some of the bright ideas received at head office and sent on to us for comment. By the time I arrived at Lucas Heights, the first laboratory work at the new research establishment had begun. A fairly large sodium loop was in operation to test the compatibility of proposed materials in the construction of a liquid metal-fueled reactor. Construction of this rig was commenced in late 1956 under a chemical engineer, Dr. RCP Bob Cairns, in a small building specifically designed for sodium work, which really means provision for emergency fast extract ventilation and no reticulated water supply. In fact, no water at all. The first major laboratory block to be built was for chemistry and chemical engineering sections. It was an expensive building because the need for active laboratories requiring a highly reliable, in fact guaranteed, non-interruptible, balanced ventilation system, extracting air through very fine filters at the rate of 20 air changes per hour. It also had a complex liquid waste system. These services required large underground ducts, which had to be excavated in the solid rock of the Lucas Heights site. The next major building housed the engineering research and metallurgy sections, and the main site workshops. Other sections had to share space in these buildings, while over the next 2 to 3 years, buildings to the house physics, technical physics, isotope and physics sections were constructed. There was a special building for beryllium work, also with an elaborate ventilation and filtration system, and buildings to house engineering design, active handling cells, irradiation rig design and construction, radioisotope production and neutron diffraction staff and programs. A major event in our early history was the start-up of HIFAR, which took place in the early hours of Australia Day, January 26, 1958. Loading of the fuel began the previous evening with the reactor tank already filled with the heavy water moderator, and with a neutron source present to initiate fission in the fuel. Fuel elements were added one by one after tests, measurements and calculations by the startup teams. There were 2 separate groups, Watson Munro doing it his way with a slide rule and a blackboard out on the operating floor, and John Parry and Colin Mackenzie doing it their way, locked in the control room free from interfering opinions. Only when both agreed were we allowed to load another fuel element, and gradually we approached criticality, the self-sustaining chain reaction. Bill Wright and I had the honour of inserting the last fuel element, number 13 as I recall. This was less than a full charge when the reactor core came to full power 2 years later. But at startup it was a clean, empty core with few neutron absorbers. Someone started a lottery on guessing the control arm angle at which HIFAR would finally go critical, and as the night wore on, the price of a ticket increased. It was very encouraging to note that the winner, at about 2 a.m. when Watson Munro announced criticality, the first nuclear chain reaction in the Southern Hemisphere, was Colin Mackenzie, who had done the calculations in the first place. The reactor was operated at low power for nearly 2 years, until early 1960, because we did not have the irradiation rigs ready, or the specimens to go in them, and we were still building the hot cells to handle the highly radioactive experiments, radioisotopes, and spent fuel elements. The timing was good, however the reactor physicists under John Simmons and the instrumentation people under George Page had opportunity for thorough testing and calibration of all the instruments and safety circuits. Also, there was time for thorough training of the first reactor shift superintendents, engineers specifically recruited for the job. The initial operation at full power, working up to 10 megawatts of heat output, was managed by the senior physicists themselves under Drs. Simmons and Parry. Well before we took HIFAR to full power, it was realised that the levels of effort and money required to pursue 2 power reactor studies were such that the research establishment should terminate one and concentrate all its efforts on the more favourable of the 2. The Commission agreed, and so, early in 1959, the LMFR project was terminated and all research effort was turned to the problems of the beryllium-moderated high-temperature gas-cooled reactor, except for that required by the growing activities of the isotope and health and safety divisions. Because HIFAR had plenty of space and ample neutrons for experiments and for irradiations to produce isotopes, we began production of high-specific activity cobalt-60, used in teletherapy radiation sources for cancer treatment, and we also undertook irradiation work for the UK Atomic Energy Authority and for the General Electric Company in England, both under contracts. The UK AEA work involved irradiating beryllium metal to see whether it would be suitable for cladding for the uranium oxide fuel in the advanced gas-cooled reactor. And the answer was no, as mentioned earlier. The GEC work involved irradiating prototype fuel elements for the first power reactor in Japan, built by GEC at Tokaimura. The fuel element was a new design, hollow, to increase the cooling surface to the coolant gas, carbon dioxide. Both of these contracts had benefits for us, earning something while we had spare neutrons. And providing experience for our own engineers in irradiation rig design. For both contracts carried staff attachments from the UK, Mr. J.C. Joe Bell for the beryllium work and Mr. Les Mercer from the GEC. Both fitted in very well at Lucas Heights, and Joe became famous amongst the staff as the founder and tutor of the Contract Bridge Club, which flourished under his encouragement. Much of this early irradiation rig work had to be carried out in temporary workshops and laboratories, which were converted construction huts, very uncomfortable in the heat of summer. Air conditioners were not provided unless the equipment needed them, and some very convincing cases were made to the administration. Most of them would not have passed informed scrutiny. Later, many of these units disappeared when the huts were vacated with the advent of permanent accommodation, to appear surreptitiously in office windows. During the late stages of the major building program, we began landscaping the site, and this became a priority task as buildings became operational because the local dust began to block expensive filters of the balanced ventilation systems. We had to import many tons of topsoil to cover the rocky site, and with it, a new variety of wildlife, funnel web spiders. Many desks were decorated with paperweights incorporating one of these embalmed in clear plastic. By the time the major building program was completed, the research staff had grown considerably in number and had been reorganised into divisions, somewhat similar to those of CSIRO, but of course all on one site and therefore more able to interact, as was necessary with most working on the one major project. This organisational change became necessary as the research establishment settled down to its active research program after the period of construction and recruitment. Charles Watson Munro had resigned as chief scientist at the end of 1959 to take the foundation chair of plasma physics at the University of Sydney, and his place as the head of research establishment was taken by Cliff Dalton, now entitled Director. It was not realised at the outset that Cliff's health was deteriorating, and he found the work somewhat stressful. So, at his request, the Commission appointed me in mid-1960 as his Deputy Director, to share the load. Sadly, Cliff died in mid-1961, and I was in the position of Acting Director for the remainder of 1961. The loss of Dr. G.C.J. Dalton was a severe blow to the establishment. He was a very well-liked and respected leader, actively involved in the research program as well as in day-to-day administration. The Commission decided in early 1962 to appoint me as Director, and by that time I had realised the shortcomings of the initial organisation, which had too many people reporting to the Director. Consequently, after useful talks with the CSIRO management, I proposed to the Commission that we should reorganise the sections, now numbering 12, into divisions. This was agreed, and we then had these divisions and chiefs. Materials: Dr. R. Bob Smith. Reactor Engineering: Mr. D. R. Bob Griffiths. Physics: Dr. J. L. John Simmons. General Nucleonics: Mr. G. George Page. Isotope: Dr. J. N. Jack Gregory. Health and Safety: Dr. G. M. George Watson. Operations: Mr. W. H. Bill Roberts, Operations Manager. Dr. G. L. Grant Miles became Assistant Director. Thus we had 6 research divisions and operations, the latter involving more than half the staff of reactor operations, site operations and engineering design sections, as well as the main workshops and other communal facilities. During a visit overseas in 1962, I examined the staff distributions within other atomic energy establishments in the UK, Canada, the USA and France, and found that all had found the same thing, that it took about 2/3 of the total staff to operate, maintain and administer the place so that the other 1/3 could do their research. So through the first half of the 1960s, the research establishment proceeded with the HTGC project, in materials, physics, engineering and design studies. These included fabrication and testing of materials and components, as the concept grew into a study of a pebble bed type of reactor, in which the fuel and moderator were in the form of beryllium oxide spheres containing dispersed uranium and thorium oxides. The use of thorium as a fertile material was to give breeding of fissile atoms within the fuel by creation of uranium-233 by neutron capture. We also looked at using some plutonium in the fuel, and the prolongation of fuel life by what is called the phoenix effect, fuel arising from the ashes. This all relied on the ability of beryllium oxide to withstand irradiation damage after prolonged exposure to high neutron fluxes, and to maintain integrity to retain the radioactive fission products within the fuel moderator pebbles. In this field of ceramics research, the AAEC program made some notable advances, particularly in the fabrication of beryllium oxide and in the basic understanding of irradiation damage and how to improve material to resist it. In 1965, 4 members of the research staff jointly won the Syme Prize for some of this work, and in 1966 a World Conference on Beryllium Oxide was held in Sydney and attracted many prominent workers from overseas to attend and present papers. This recognition was achieved by teamwork. Although obvious credit goes to the authors of papers and the winners of prizes, there was a tremendous amount of support by others. For example, the irradiation testing of samples of the oxide and of prototype fuel dispersions relied on the engineers to design and construct complex rigs to go in the research reactor HIFAR. The rigs required sophisticated instrumentation and control systems. The post-irradiation examination of highly radioactive specimens is a skilled speciality, involving micro-examination of cut and polished sections, and all carried out in the hot cells by remote control with manipulators. The chemists were required to develop and supply as services analytical methods at levels of purity not encountered elsewhere. The decisions on purity and on fuel moderator fertile element compositions involve the theoretical and experimental reactor physics, and the whole program with such materials operated under strict control by health and safety personnel. Add to this the operation of HIFAR to suit the demands of the irradiation experiments, the work of the site operations staff handling ventilation, effluent treatment and disposal, and so on. And it is clear that close integration of many professionals and their facilities is required to run a project-type operation such as this research program. I must emphasise that at all times the Commission management did not lose sight of the basic objective of this program, the creation of the cadre of experts for the future development of atomic energy in Australia. Indeed, we were reminded of this annually. One of my annual tasks was to be in Canberra, accompanied by Mr. A.J. Burt Moulding, our Director of Finance, during Cabinet discussions of the federal budget, ready to brief the Minister on our submission for funds for the ensuing year. It was always made clear to us that the program was not to become an end in itself, and this was always reiterated every couple of years when we submitted a forward-looking program proposal at the request of Cabinet. I do recall the Minister asking at an early date what it would cost if we were to build a prototype power reactor or reactor experiment based on the results of our work. It was Sir William Spooner, an accountant by profession, and I replied that we had not really worked that out because the work was at an early stage, but that based on overseas experiences, I would estimate not less than £100 million. For a moment I thought I'd caused a Cabinet Minister casualty, and once more it was emphasised perhaps even more strongly that what we were doing was for training and experience, and that we were not to get any big ideas beyond our charter. Having said all this, there is no doubt that the Chairman of the Commission, Sir Philip Baxter, always hoped that the product of our efforts would be a design of a power reactor particularly suitable for Australian conditions. He had in mind particularly that the favourable nuclear properties of beryllium, the low neutron capture, good moderator, neutron enhancement characteristics could favour a small reactor design, while the high coolant temperature should lead to a high thermal efficiency and therefore minimise the amount of waste heat to be dumped, so needing less cooling water or even allowing air cooling. Unfortunately, these ideas came to be treated by some people, and particularly some journalists, as the justification for the AAEC research program. They were never so. But when, in 1966, we reported to the Commission that the HTGC did not seem to be a promising potential competitor for some already established systems, such as the Westinghouse pressurised water reactor, the forerunner of many of the PWRs now in service around the world, and the research program was changed, we had for the first time the criticism that the Commission had lost its way. By that time, several power reactor types being developed overseas, particularly in the USA and the UK, were becoming commercially successful. Any new system would have to have outstanding performance to compete, and we had found that the predicted fuel burn-up was lower, and that the fuel reprocessing costs were higher for the HTGC than originally expected. So we recommended that the project should be terminated. There is no doubt in my mind that the program from 1956 to 66 did exactly what it was designed to do, to produce a cadre of experts. That it did was so clearly brought out later in the ill-fated Jervis Bay nuclear power project, but that comes a bit later in the story. As a result of the report on the HTGC, the Commission decided to phase out research on gas-cooled reactor systems and undertake work on water-cooled and moderated reactors. With particular emphasis on heavy water systems, the research establishment was required to submit proposals consistent with the forward-looking prospects for the application of nuclear power in Australia, which had changed considerably since the initial program was devised. In particular, the program was to encompass studies of fuel fabrication and behaviour, selected with a view to the eventual use of Australian-produced reactor fuels. The reason for selecting water-cooled systems was simply that they appeared at that time to be the frontrunners in nuclear power technology throughout the non-communist world. Although the UK and France had developed and applied gas-cooled reactor technology on a large scale, it was becoming clear by 1966 that pressurised water reactors, PWR, boiling water reactors, BWR, and heavy water reactors, HWR, were well on the way to being the favoured systems for the future. The reason for emphasis by the Commission on heavy water systems was simply that Canadians had shown that they could be run on natural uranium, i.e. not enriched in the uranium-235 isotope, and the idea of fueling the Australian reactors with our own uranium, processed at home, was attractive. The PWR was first developed by Westinghouse in the USA, and its technology had a flying start by being selected for the US Nuclear Navy. The first nuclear ship, the submarine Nautilus, put to sea years before the first civil PWR, the shipping port reactor, came online in the United States. The main competitor to Westinghouse, General Electric, developed a rival power system for the second submarine, the Seawolf, based on sodium cooling. But the system had problems with leakage and was abandoned. GE turned its attention to water-cooled systems and took up development of a system pioneered by the Argonne National Laboratory near Chicago, which had developed a method of obtaining high output from a light water moderated pressure vessel reactor by letting the water boil in the reactor core and taking direct steam to turbines rather than using cooling water to raise steam in secondary water in a heat exchanger boiler as in the PWR. There are many boiling water reactors in the world today. The Canadians, from the very beginning of nuclear technology in the 1940s, put their efforts into development of reactors moderated and cooled by heavy water, and Canada has a large nuclear power program based on heavy water reactors. Heavy water is chemically identical to ordinary water, but quite different in nuclear properties. Water is hydrogen oxide, and about 1 in every 5,000 hydrogen atoms in nature is heavy hydrogen, called deuterium, which has an extra neutron in its nucleus. Canada has developed quantity extraction methods for producing heavy water from natural water. It is an expensive product, but it is a very good neutron moderator, so much so that the power reactor using it can run on natural uranium, whereas PWR and BWR systems require enriched uranium, in which the natural mix of 1 part in 140, 0.7%, of the atoms being fissile uranium-235 has been increased to 2 to 4%. We shall look more closely at uranium enrichment later, but in a sense, Canada chose to enrich the water rather than the uranium. One reason for the success of the various water-based systems right from the beginning was their electrical generating systems ran on existing established technology. Not quite so, in one sense because fossil-fueled fired boilers had long since been developed to produce superheated steam, and raising steam from a water-cooled reactor did not easily permit superheating. So it was necessary to resurrect old technology running turbines on wet steam. One attraction of gas-cooled reactor systems has always been the possibility of higher steam temperatures and hence higher thermal efficiencies. And there are still development programs towards this end in the USA, Japan and Germany. End of Chapter 5. Thanks for listening. The next episode of Australia's Uranium Opportunities covers Chapters 6 and 7. This period, in the second half of the 1960s, tells the story of the AAEC and their change of program to focus more effort on light water reactors, which appeared at the time were going to dominate the market. The start of a secret Project Whistle into uranium enrichment, and a discussion of reactor power coefficients, which played a causal role in the Chernobyl disaster. Continued secondments of Australian staff abroad were supported, along with programs hosting international staff and students domestically. Indeed, US nuclear royalty, Dr. Alvin Weinberg, makes an appearance.